All right, everybody, welcome to the fifth and final week of this first R phase of Geography 473 673. I will be covering R in a lot more detail in the advanced R section of Geography 473 673, which occurs in the spring semester. So, this is our last week of R, and what we're going to be doing for this week is reprojecting and writing rasters. So, we talked a little bit last week about how sometimes rasters can come in weird projections, and even though we didn't play with any last week that had anything other than a basic latitude-longitude projection, sometimes that data can come that way. So we're going to handle reprojecting and writing rasters this week, and also resampling. And so what this means is getting a specific raster to a more desired resolution and how you would go about doing that. Before we touch on that, I just wanted to go over one more essential skill, and I know we've already talked about this, but I really wanted to cover this again. So I'm going to open up RStudio, and let's talk in a little bit greater detail about indexing. So I'm going to have this matrix, mat A, and it's just a nice matrix, a sequence of numbers 1 to 16 with 4 rows and 4 columns. So this is our matrix. This is how it's structured. Let's grab the second row, third column, the value from the second row in the third column. And we see that that number is 10. And if we go over second row and go over to the third column, we see that the number is 10. What if we wanted to grab a very specific few grid cells, and that being points from the first row and third row, and the second column and the fourth column? So just to give you an idea, just what this concatenation looks like, 1, 3 is just 1, 3, and then 2, 4. So let's go ahead and throw that in there. So we have 5, 7, 13, 15. If we go over here, if we go over here to the first row, 1 right here, second column, we see we have a 5. And then if we go to the third row, 3, and the second column, see we have a 7. Same thing with this fourth column over here. We have 13 and a 15. Now you can also just select rows 1 through 3 and columns 2 through 4. And remember, we do this via the colon operator, which gives us a sequence. And so now we have this image right here, which is just this subset, this subselected matrix of right here, this top right corner, this 9 by 9 matrix. We can remove this column selection and just leave it blank, and that will assume we want every single column. So we are just selecting rows 1 through 3, and then when we leave it blank after a comma, that means we want every single column. Vice versa, we can have comma 1, 3, and that will give us every row associated with columns 1 through 3. So what we have here is just a nice example of how to index and what is going on, all from this original matrix mat A. And notice once again that the subselection is done via these brackets. So bracket, row, comma, column. So now what I would like you to do is actually go and replace values in this following matrix. So for example, if we want to change this 1 to a different value, we could just say 1, row 1, column 1 equals 77. Now we reprint mat A, 77. I want you to recreate, starting with that blank matrix, create this oddly represented matrix that doesn't have a whole lot of conformity to it. So go ahead and try and make that, and I'll give you a hint. There are some shortcuts along the way that you can take using the colon operator. On to rasters. The data set that we're going to be working with this week is global temperatures averaged from 1961 to 1990. So this is a netcdf file that can be found in your datasets folder, and we're going to be using the raster package, a raster viz package, viz for visualization, and map tools. Let's copy all this over, get rid of that matrix stuff, and notice what's going on here. So we talked about the shortcut in the last tutorial, how we can read a netcdf file directly into the raster function. So we're doing that, but notice that we're also adding a few extra things here. A var name, a variable name of temp, and the first band. So what is going on here is, let's throw this open, and I need to load my packages first, and then go through with that, and boom, here we go. So now let's take a look at this, what's going on. In the names here, we have global 1961 to 1990 mean monthly surface temperature climatology, with the z value of equal to 1 and the variable equal to temp for temperature. If we were to actually open this up, let's just say nc file equals cdf4, nc open, and then let's copy over this and just load it up directly. You notice that, okay, yeah, here's our long name of our variable. Our short name is temp, which has the dimensions lon, lat, time. The units are Celsius, okay, that's all good. Then we have, notice the dimensions here now. So far, we've only dealt with files that have one snapshot in time. For this, we have a time size of 12. So we have 12 different months, or 12 different bands. So each of these bands can be thought of as a layer within this stack of temperature data. We're grabbing the first layer, or the first georeferenced band of temperature, which is January. So we are reading the variable name temp from this netcdf file, and we're just grabbing the first time slice. And why is this? Because this is a three-dimensional matrix right here. Because we have all of these different time variables. So far we've only had a two-dimensional matrix to worry about. Now we have a three. So a raster, remember, is a two-dimensional matrix. So we need to just subselect one specific time right here. That time is January. So let's rerun this, open it to raster, and notice we already have some really nice things. We have the band, one of 12 bands, so that's January. We have our extent, which just covers the entire globe. We have a resolution 5x5 with dimensions 36 by 72. So pretty coarse data set compared to the ones we've been working with. But I mean, back in the day, even 20 years ago, this was state of the art. So we're going to create a new raster that is a little bit finer resolution. We're going to give it, so notice our dimensions here. We have 36 rows by 72 columns. Let's give it a n row of 180 and 360, and then let's take a look at this new raster we're making. Okay, so we have an automatic projection put in. We have the automatic extents of the globe. Our resolution is a lot higher here now with larger dimensions, larger number of cells. And now we need to plug this data, and we need to resample this to this new size. So remember, if we run an image on this temp clim, pretty coarse. It's really hard to make a lot of sense of what's going on here. We do know that these longitude and latitude values make sense. We expect it to be hotter around the equators. So that makes sense. And if you wanted to take a look, there's no data in new raster yet. So there's no data. But there is an extent with a size, dimensions, number of cells. So what we want to do is we want to resample the data in temp clim to the size of new raster, using the bilinear method. So we're going to use the resample function here from the raster package. And let's run this. So now look at this. So we have a set number of values here, -48 and 32. This makes sense, it's January. Temperature doesn't get too high. And remember, this is also Celsius. So we have this data set right here. This is a kind of a reasonable temperature values for this, so we know that we probably don't have to do a whole lot of data quality control here. It's probably good to go. We have our coordinate reference system is the same as it should be. Our extents are the same as they always were, but now look at this. Our dimensions and our resolution. Our resolution is now 1 by 1, just the same as this new blank raster we made. But that comes from a 5 by 5 resolution. So we went from 25, almost 2,600 cells to 64,000 cells. 64,000. So 2,600 cells to 64,000. So we greatly enhanced this resolution. So let's go ahead and do an image on Resampling now. Look at how much smoother that is, and I'll compare these. And so this is what happens when we resample bilinearly. And so now we're actually taking a look at, okay, we're starting to see the shape of North America here, Atlantic Ocean, and then Europe, and then India over here, China right here, Russia up here. So we're kind of getting a little bit better picture of what this data is. So that's how you would go about resampling. And all we did is we just created this blank raster called new raster, which had a set size of 180 by 360, had the same extents, had the same coordinate reference system, which meant that we could use the resample function to just resample temclim and all of the data inside it to this size with the bilinear method. And you can actually go into resample, and you can get a list of what these arguments are saying and what's going on here. So now let's get into new projections. Let's say we have a new projection. We're going to use the CRS string to give this proj4 string to this CRS function. And let's go ahead and run a help on CRS, and notice that we actually have multiple sets here from multiple different libraries. We're going to be using this one. They're probably just about the exact same function. They just come from different libraries. That happens sometimes. But I have this note up here that whenever you load map tools, the SP package is also loaded as downstream because of your loading map tools. So let's click on that one. And we have proj_args, which is a character string of projection arguments, aka our proj4 string. So let's go ahead and let's run that, and let's see what it's looking like here. Okay, boom. So there we have our CRS arguments right there. That's our new projection. That's what the string is going to look like. Let's project our resampled temclim to that new CRS. So all we're going to do here, we're going to create a new variable, proj_temclim, and we're going to use project raster. Let's do a help on project raster. We see we have from the raster object, we're going from to, or in this case, we're just going to hand it the CRS. So we're saying, hey, we're going to give you this resample, which is just the raster. It's the only raster object that we need because we're not reprojecting to a new raster projection. We're just projecting to a new CRS projection. We don't need another raster for this operation. So let's resample that, and let's take a look at it. So first off, we notice a warning that pops up. Most warnings you can ignore. You can ignore this one too, but this is an important warning just to provide you with some information. So we're projecting from lat long to a Robinson projection. Now, Robinson projection is trying to accomplish a better representation of the curvature of the Earth than the lat long does. So there are projected points that are not finite because some of our lat longs will not be visible using the Robinson projection. And now notice our extents as well. They are all over the place because we're not in degrees latitude and degrees longitude anymore. So likely these are meters from the prime meridian and meeting the equator. So, and actually the reason that I know that is because up here in the projection arguments you have 0x and 0y units meters. So now if we run an image on Reprojecting, I go back, look at how it's a little bit warped near the poles now. And so this is more realistic in all honesty because, yeah, it's an oblate spheroid. That's the Earth. And notice that we go from degrees latitude and degrees longitude to meters from the prime meridian or the equator. So we just reprojected that using the project raster argument right there. And if we wanted to, we can actually make a nice image of this. And even though I talked about incorporating your own shapefile because the last one wasn't quite pretty enough, we can just use this world simple for this because we are so zoomed out. We have an image here of the temperature for the entire world. We're going to use the blue-red theme, and we're going to give it a title of January Global Temperature, averaged from 1961 to 1990. And then we'll add those coastlines to that with world simple. Go ahead and plot that up. And there we go. There's Canada, USA, Brazil, Russia, China, African continent, Europe, European continent. So this makes total sense. And notice here that I did not plot my projected temclim. I just plotted my resampled temclim, which still has longitude, latitude CRSs. And that's why you see this latitude over here and this longitude over here. Now what I can do is the reason that I had to do that over here, the reason I had to use res temclim is because guess what? That is the projection default of world simple. So if I actually print out a quick summary of world simple, look at that CRS, the exact same. So what happens if I really like this reprojected and resampled version of this? And I want to plot this. I want to plot Reprojecting. So let me copy this down. And we need to replace this, right? But now hold on. World simple is a longitude latitude projection. If I go to Reprojecting, we're in Robinson. So we are going to need to reproject world simple. The way that we would do that is using spatial point transform. So what I can do right here is I can redefine world simple using the spatial point transform, and let's do a help on that. And remember, we're on the SP package here. So all it needs is an object to be transformed and an object of class CRS. So I'm redefining this, and this is actually redundant. I already did this above when I defined the new proj in line 15. So all I'm doing here is X is world simple, that's our object to be transformed, and then our CRS object is that. Enter that, and now it's printed out. Boom. Now we have a Robinson projection. We have our X-min and X-maxes, which makes sense because we're in meters from prime meridian and equator. And now, when I go and plot this up with our new overwritten world simple, we get this more realistic distortion along the poles with this matching temperature data set. So this is exactly one, and notice that along the limits and the axes along the outside, we are still in meters from center point. So that is how you would go about doing that. taking a step back from rasters specifically, so far we've been making all of these plots, and what some of you have noticed is that you can just download, you can save this image right here, and you can export it, you can save the image, you can go ahead and do all that. But what you can also do is a little bit more formal way, where you can actually get a little bit more specification and customization. So what you can actually do is you can use this PNG function. And when you spawn the PNG function, any plot that goes within PNG function and dev.off, which cuts off the PNG function, all that plot is going to go directly to a PNG. So in the PNG function, it's a base function, so it comes from this file name right here. We give it a width and a height of our image, and we give it units, and we give it a resolution. And then we just throw our code in here that we just used to plot to make this image over here. And this is being put into my downloads folder as mypng.png. Run that line. And now it didn't pop up over here, but now, because I closed it, if I go over to my Finder, I'm going to Mac Reminder, and I go to Downloads, and right at the top, my PNG. So now I save this image, now I can upload that or share it or do whatever I want. So that's an example of that, and it can be very useful if you don't want to just use the export right there. So the other option we have here, if we want to save this data, let's say we want to save this data set. We don't just want to save the PNG, we also want to save the data set. Now we can do that using the write_raster function. So with the write_raster function, you actually have multiple output formats. So if you, let's say you get a data set, and your data set is in netcdf, just like ours was all the way up here at the beginning. And you need to convert that to a geotiff. But first, you need to do all this resampling and reprojections. And this is how you would go about doing that. So if with the write_raster, you need a raster object, x. You need a file name. Mine is going to be projected temclim 1961-1990.tiff. A format, so you can see this write formats, and we need gtiff right here. So we have gtiff right here is the format because we're going to save it as a geotiff. We give it a variable name, a long name, an x name for lon, and a y name for lat. Now this is actually incorrect because we're using our projected temclim, so these should actually be meters and meters. So let's go ahead and run that, and simple as that, just as fast as that. Here's our geotiff, and if we want to actually open that up, we can just say x equals raster, pop that open, and I save this projected, and now I can run image on x, and boom, there's my raw data that I just reprojected and resampled and saved. So that's how you would go about doing that, and you can save, just as a reminder here, you can save these as any of these write formats. So you can save it as a native raster, which is .grid. You can save it in ASCII. Save it as a netcdf, which you just plug in CDF in there. Saves it as an NC extension, an NV, an Esri, and .img. You can save it all these, and that can really make things easier down the line. So that concludes this tutorial. For this week's assignment, what I'd like you to do is, using that data set that we just played with, extract the data for January and July. Find the difference in temperature between those 2 months globally. Enhance the resolution 2 times using the nearest neighbor method. And remember, if you need help there, do a help on resample. Plot in a mole-wide projection using this proj4 string right here. Output that raster to netcdf using that write_raster function. and then upload a PNG and the netcdf file to Canvas under week 5 assignment. So that's it. That concludes this introduction to R, and I hope you enjoyed it, and I look forward to seeing your assignments.